In this video, we're going to introduce connected metric spaces. A reference for this material is the book by Rosenlicht, Introduction to Analysis, Chapter 3, Section 6, on connectedness. So the definition is that a metric space E is said to be connected if the only subsets of E which are both open and closed in E are E and the empty set. Now remember that in any metric space, E and the empty set are open and closed. So this is saying that the only subsets of E which have that property that they're both open and closed are those two sets. Okay, and a subset S of E is said to be a connected subset if the subspace S is connected. So just to clarify what that is saying, so if you have a subset of a metric space, that subset can be given the structure of a metric space. It's the induced structure of a metric space as a subset of a bigger metric space. And we say that this set S is connected if it is a connected metric space. That's what that means. Because in the first sentence, the word connected refers to a metric space, not just a subset. So the second sentence is saying that if you just have a subset, okay, that is a subset of a bigger metric space, then we say that that subset is connected if when you give that subset the structure of a metric space, that metric space is connected. So this definition might be not very intuitive, but there is a way to give an equivalent definition that is more intuitive. So here's a lemma. Let E be a metric space, then E is not connected if and only if E can be written as E equals the union of two subsets A and B, where A and B are disjoint, non-empty, open subsets of E. So let's prove this. This essentially follows from the definition. So suppose that E is not connected. Well, what would that mean? Connected means that the only subsets of E which are open and closed are E and the empty set. So what would it mean to be not connected from the definition? It would mean that there is a subset of E which is open and closed, which is neither E nor the empty set. That's what it would mean to not be connected. So then there is an open and closed subset, say A, of E, which is neither E nor the empty set. So such that A is not E and A is not the empty set. So you have your space E, you have your non-empty open subset A. How can you rewrite E as A union B? Well, of course, we should take B to be the complement of A and E. So let B be the complement of A and E. So this is my notation, and A with the superscript C for the complement. Then B is open. Okay, why is it open? Because A is closed, and the complement of A must be open. So therefore B is open. So being the complement of the open set A, and B is also closed. Oh, well, we don't actually need that in the lemma. So B is open, and B is non-empty. Okay, why is B non-empty? Well, because A is not equal to E, right? A is a proper subset of E. Because A is not equal to E, so A is a proper subset of E, so it has a non-empty complement. So B is open, non-empty, and why is it disjoint from A? Well, because it's the complement of A. So A and B is the empty set, and E equals A union B. Okay, let's just erase the ands so we don't have too many ands. Okay, so that's one direction. And then for the converse, so conversely, suppose that E can be written E equals A union B, where A is where A and B are disjoint, non-empty open subsets. So we want to show that E is not connected. Well, what it means to be not connected is that there exists. So to be connected means that the only subsets of E which are both open and closed in E are E and the empty set. So we want to show that there exists a subset that is open and closed, which is neither E nor the empty set. Well, we would take A, for instance. So then A is open, non-empty, and since B is non-empty, so A is non-empty and open, since B is the complement of A and B is non-empty, A is a proper subset of E. So A is an open, non-empty, proper subset of E. That implies, the fact that A exists implies that E is connected. So that's the proof. So for instance, it's easy to come up with non-connected sets. So if you're in R2, you just take, how about the disjoint union of two open sets in R2? Then this union is not connected, right? Okay. By the definition, by this lemma. So let's make sure we understand what we would have to do to show that a metric space E is connected. What would you have to do? So by the lemma, E cannot be written, right? To be not connected means that there exists a decomposition of E into two disjoint, non-empty, open subsets. So to be connected by the lemma means that there does not exist such a decomposition. one way to think about that is that if you write E as the union of A and B and B are disjoint and open, then one of them must be empty. So let's write that down. So to show a metric space E is connected, what you can do, so this is for understanding how to prove that something is connected. You can suppose that E is A union B, where A and B are open, and you need to show that one of these is the empty set and one of them is E. So show that either A or B is the empty set. And remember, when we're trying to show either A or B is empty, you can suppose that A is not empty and then show that B is empty. So for instance, you can suppose that A is non-empty and show that B is empty. So this is just writing down the proof technique based on the definition of connectedness. Well, it's actually using the lemma, right? But it's just spelling out, if you want to show that something is connected, what you can do. Okay, let's prove a little proposition. So this is about the real number line. So if A, B, and C are real numbers, we say that C is between A and B if either A is less than C and C is less than B, or B is less than C and C is less than A. So the proposition is any subset of R which contains two distinct points, A and B, and does not contain all points between A and B, is not connected. So here's the picture, here's the number line, and suppose that A is less than B. So suppose that you have a subset that contains A and B, but it doesn't contain everything in between. So for instance, let's say that there's a point C which is somehow missing in your set. Then your set is not connected, which intuitively makes sense because you're just missing a point here. So the fact that you're missing a point intuitively will split up the number line into two disjoint open sets. I mean, that's basically the proof. So let's prove this. So how would you show, we want to show, so let S be a subset which contains two distinct points, A and B, and does not contain all points between A and B. So suppose that S is such a subset, and let C be between A and B such that C is not an S. So such a point C exists by hypothesis. So we want to show that S is not connected. Well, by the lemma, to show that S is not connected, we can write we can show that we can write S as the union of A and B, where A and B are disjoint non-empty open subsets of S. So if we can do that, then we're done by the lemma. Well, how can we write S as the union of two non-empty disjoint sets that are open? Remember, S is a subset of R, right? So to be open means that it's the intersection of an open set in R with S. So the natural thing to do is to note that S is S intersect all points that are less than C and all points that are greater than C. That's because C is not an element of S. So every element of S must be either greater than C or less than C. So therefore C is the union of these two sets, which are obviously disjoint, right? Because these open intervals, the set of X and R such that X is less than C, and the set of real numbers such that are greater than C, these are disjoint. So I've written S as the union of two disjoint sets, and this expresses S as the union of two open subsets of S that are disjoint. And how do we know that these subsets are non-empty? Because we suppose that A and B are in S. So since A is less than C and A is in S, okay, this first set is non-empty. And since B is greater than C and B is in S, B is contained in the intersection of S and the set of real numbers that are greater than C. So therefore we've written S as the union of two disjoint open subsets of S. Disjoint non-empty open subsets of S. Therefore, by the lemma, S is not connected. So that's the proof. Notice that we aren't saying that a closed interval is connected. Okay. We're just saying that if you had an interval that was missing a point in between, then that cannot be connected. That's very different from saying that if you have all the points in between, then it must be connected. And we will show that, in fact, it is true that if you have an open interval